We return now to our full system, and we will now consider the completely arbitrary case where we do not have azimuthal symmetry and where we're looking for the solution to the associated Legendre differential equation, which, as we've stated, is solved by the associated Legendre functions, which have this form. As opposed to the ordinary Legendre polynomials, the associated Legendre functions have two indices, L and M. These are sometimes written as sub Lm. Here we will do L and M superscript. So this is not an mth power. This is just an indexing system. The mth associated Legendre polynomial operating on argument x is going to be given by this expression, which itself can be written as the mth derivative in x of the ordinary Legendre polynomial of degree L. Just as we had with the original Legendre polynomials, there is a symmetry to these where the p sub L negative mth associated Legendre polynomial is equal to negative 1 to the m of times L minus m factorial over L plus m factorial times the p sub L positive m associated Legendre polynomial. The associated Legendre functions are a set of complete orthogonal functions on the domain -1 to 1. What does that mean? If we have a set of functions, phi sub k of x, this set is complete over a domain x in A to B if for all piecewise continuous functions f of x defined on the same domain AB, we define an error epsilon sub n, which is the L2 norm squared of the difference between f minus the summation from I equals 1 to some value n of coefficients c sub I times elements of our complete orthogonal system. This system is complete only if, as n goes to infinity, this error can be driven to 0. So put another way, this orthogonal set of functions will act as a true infinite dimensional basis for any function f defined on the same domain covered by this system, because we can always rewrite that function f as a weighted sum of these functions phi k to arbitrarily precise levels if we take more and more of these functions. The associated Legendre polynomials are exactly an example of this type of complete orthogonal system. And therefore, just as we did before, we can write a normalization for any pair of degrees L prime and L. We can write the integral from -1 to 1 of P L prime M of x times P L M of x as 2 over 2L plus 1 times L plus m factorial over L minus m factorial times the Kronecker delta in LL prime. If we further combine the angular terms represented by the functions phi and theta, this gives us what are known as the spherical harmonics. These functions YLM, that are functions of theta and phi only, and are given by this normalization multiplied by the associated Legendre polynomial in cosine phi times the complex exponential, which we got from our very first separation of variables when dealing with Laplace's equation in spherical coordinates. The spherical harmonics have the property that the harmonic L negative m is equal to -1 to the m times the complex conjugate of YLM. We choose a normalization of this set so that it is once again a complete orthogonal system. And that means that we can write the normalization over the full ranges of these two parameters, which is 0 to pi for phi and 0 to 2 pi for theta, of YLM times the complex conjugate of YL prime M prime must be the Kronecker delta in L prime L times the Kronecker delta in M prime M. Remember, the zenith angle is only defined between 0 at zenith to pi at nadir and has this differential element, which gives us the form of this integral. As an additional note here, in the case where m is 0, which you will recall corresponds to the azimuthally symmetric solution, we get that the YL of mth harmonic, or rather the YL 0th harmonic, is equal to the square root of 2L plus 1 over 4 pi times the regular Legendre polynomial P sub L of cosine phi. So these zeroth order harmonics give us the azimuthally symmetric solution and should collapse back down to something equivalent to the Jeffreys number representation of our full function. As before, we have to set all of the ALM components to 0 such that we get u going to 0 as r goes to infinity. And so the only thing that is left is the summation from L equals 0 to infinity over the summation from m equal to negative L to L of coefficients BLM times r to the negative L plus 1 power times the mth spherical harmonic. So this now is a complete representation in series form of our potential function as a function of the coordinates of our body in orbit around the extended body. And now we have to insist that these spherical coordinates are given in a rotating frame such that the BLMs represent the specific mass distribution of that body. So how do we get to these BLM coefficients? Let's recall our original problem statement. We posited some inertial frame, we posited a coordinate set for our orbiting body M2, and we posited a coordinate set of different spherical coordinates for the differential mass element dm within our extended body, both of these vectors with respect to the same inertially non-accelerating point O. And we found that we could write the denominator, this term, r dm rel 2, that arose within our potential description as an infinite summation of Legendre polynomials. Here, we are going to introduce something known as the Legendre addition theorem. The nth Legendre polynomial of a unit direction x dotted into a unit direction y, each of these representable by sets of spherical angles, is given by 4 pi over 2l plus 1 times the sum from m equals negative L to L of ylm, the spherical harmonic Lm, operating on the two spherical angles defining unit direction x hat, times the complex conjugate of that same harmonic operating on the spherical angles defining y hat. In this case, we have x hat represented by the theta phi coordinates of our original setup, and y hat represented by the lambda beta coordinates of our original setup. And so this denominator, which you will recall was originally a function of cosine beta minus phi, can be rewritten in this form as an infinite summation of pairs of Legendre polynomials and their complex conjugates in these two different coordinate sets. We can therefore find the BLM coefficients by matching terms of these summations, where UR theta phi has to be equal to this triple integral, where we can substitute in this series and then match it against the series on the previous slide. And from this, we can define something known as the multipole moments. Q of Lm is equal to the triple integral over the body's volume distribution under the assumption that we have a density function of the body gamma of pairs of spherical harmonics and their complex conjugates, and these additional terms that give us the form of this original integral expression. This is incredibly abstract, so let's look at some specific cases to make sure that we understand what this is telling us. In the case where L is equal to M is equal to 0, which is known as the monopole term, our leading coefficient is equal to the triple integral over the density function gamma times rho squared sine squared beta d rho d beta d lambda, which will be equal to the total mass of the entire body. And so the leading term of our potential is still just Gm of the body divided by r, exactly the same as in the azimuthally symmetric potential. The leading term has to be our central body potential because the entire point of this exercise is to get all the rest of the terms of this series, which act as the perturbing forces. The other terms, the BLMs, are related to the multipole moments as G, the gravitational constant, times 4 pi divided by 2L plus 1 times the multipole moment QLM. We return now to our body fixed reference frame representation of this coordinate system, where O is the center of mass of our extended body, and theta, phi, and r are the spherical coordinates of M2 with respect to that center of mass. And now if we represent the position of a mass element of this body with respect to its center of mass via Cartesian coordinates c, eta, zeta, then we can get these expressions for the leading terms of our potential function, where the monopole terms, those are the ones with degree 1 and order 0, have this form and must equal strictly 0 due to the nature of this integral. And the dipole terms, those are the ones with degree and order 1, have this form and must also be equal to 0. In general, then, we can write the potential function of our central body acting on the orbiting point mass M2 as the gravitational constant times the mass of the central body divided by r. So we always have mu over r, this leading term, that is our central body potential, plus the gravitational constant times the infinite summation from L equals to 2 to infinity, because we've knocked out the first sets of terms, over the summation of m equal to negative L times L of the qlth multipole moment times the orbital radius to the negative L plus 1 power times the spherical harmonic YLM of the coordinates of the body theta and phi, again being measured from a body fixed direction. Most commonly, this is represented in this form, where we again pull out the GMB over R factor, and inside this multiplication, we have the one term corresponding to this times the summation over the equatorial radius of a body divided by the orbital radius magnitude to the lth power times the lth mth Legendre polynomial operating on cosine of the zenith angle multiplied by cosine m theta plus sine m theta with some coefficients, CLMs and SLMs, and these are the coefficients that are most commonly tabulated. If we briefly return to the specific case of azimuthal symmetry, you will recall that we had U of R phi was equal to GMB over R times the quantity 1 minus the sum over the Jeffreys numbers from 2 to infinity of the equatorial radius divided by the orbital radius to the kth power times the kth Legendre polynomial in the cosine of the zenith angle. Compare this to the general equation, and remember that the zeroth spherical harmonic was just the square root of 2L plus 1 over 4 pi times the lth Legendre polynomial in cosine phi. We get that the lth zeroth multipole moment is equal to negative the square root of 2L plus 1 over 4 pi times the mass of the body times the lth Jeffreys number times the equatorial radius to the lth power. This is the azimuthally symmetric subset of the multipole moments. And the one corresponding to J2, that dominating term for many bodies, Q02, directly corresponds to J2 within some normalization. And this is what's known as the quadrupole moment. Because of the importance of the azimuthally symmetric terms, frequently you will come across a form of the potential that specifically pulls them out and also leaves the Jeffreys numbers in their original form. And so we can rewrite the equation on the previous slide as this, where mu here is explicitly the gravitational constant times the mass of the central body, r is the magnitude of the orbital radius, and then this is all multiplied by 1. This is our leading central body potential. This is the potential of the pure two-body problem. And then everything else here is the perturbing potential. And we've collected all of the azimuthal terms in here, and then all other terms in this double summation. Where you'll notice now, in this interior summation, m goes from 1 to L. Previously, it was from 0. That's because the m equals 1 terms are now captured in this summation here. The nomenclature is that L is the degree of the spherical harmonic or multipole moment, or the potential function equivalently, and m is the order, and the azimuthal terms, the J sub L terms, the things for m equal to 1, correspond to zonal harmonics. And these are best understood as bands of latitude. J2 being the equatorial bulge, J4 being the two bands around it, and so on and so forth. So J sub L, by the conventions that we've set up, is exactly equal to negative the value of this coefficient CL0. Orthogonal to this are the sectoral harmonics. These are bands of longitude, and these correspond to the subset of terms where L is exactly equal to M. And finally, everything else, all of the cases where L is not equal to M and neither one is equal to 0, these represent the tesseract harmonics. And these are tiles of latitude and longitude. And the higher the degree and order, the finer the gridding gets. And so as you go to infinity, as L goes to infinity, you can describe smaller and smaller features of the potential of your body. So in order for any of this to be useful, we need values for these coefficients, for the CLMs, SLMs, or these coefficients plus the Jeffreys numbers. And the way that we measure these is by tracking the deviation of orbiting bodies from their ideal two-body paths, and then accounting for all other perturbing forces in order to isolate the effects of just the perturbing potentials. This is most easily done by putting something in orbit around the planet. And we have many such assets orbiting the Earth right now as we speak. One of the most ubiquitously used data sets is derived from something known as GRACE, the Gravity Recovery and Climate Experiment. Originally launched in 2002 with an original 5-year mission, it actually lasted for 15 years. And in 2018, a follow-on, GRACE-FO, was launched, which is now continuing GRACE's mission. This system is composed of 2 identical spacecraft that fly along the same orbit and track each other in the new version via laser ranging between the 2. And what they provide by detailed tracking of their position, both relative and absolute as provided by the GPS constellation, are continuous updates of what is known as the gravity anomaly, those SLM-CLM coefficients, typically on a monthly cadence between degrees 60 and 90, but in the full data set, up to a degree of 2190. So we are literally able to measure the coefficients of the potential of the Earth up to almost 2200 degrees of spherical harmonics. And we are able to provide monthly updates of those coefficients for up to 90 harmonics. You can get all of this data. This is publicly available and is hosted by both the International Center for Global Earth Models and the United States National Geospatial Intelligence Agency. These are used to build up standard models, and the current standard is known as the Earth Gravitational Model 2008, which was first published back in 2008, unsurprisingly, but has been updated several times since then. And in addition to this, there are literally dozens of other models built on these and other data sources and combining space-based measurements and ground-based GPS measurements and topographical measurements and you name it to provide specialized models for different purposes.